Welcome back to Basic Mathematics. In this video, we're going to be taking a look at operations on signed numbers. The signed numbers, or integers, that we've talked about before, take the whole numbers and allow us to introduce positive and negative variations on those numbers. By doing this, we gain access to solutions to subtraction problems that we couldn't solve before. It also opens the door for a couple of nice features in mathematical modeling. So without further ado, let me get my head out of the way and let's dive in a little bit. So the integers or signed numbers are the positive or negative whole numbers. Thinking about this in terms of a number line, if we set 0 in the middle, we can count towards the right with 1, 2, 3, 4, and so on. We can also count towards the left with -1, -2, -3, -4, and so on in that direction. The opposite of a number has the same value, but a different sign. So for example, -1 and 1 are opposites. 1 is the opposite of -1. -1 is the opposite of 1. They both have the value of 1. -1 is negative, 1 is positive. Similarly, we can look at 2 and -2, 3 and -3, 4 and -4. 0 is kind of an interesting case because 0 is its own opposite. 0 is neither positive nor negative, and in order to make the rest of math work out and the language of math work out, we generally say that the opposite of 0 is 0. To make things confusing, the opposite of operation, the negative sign, and the subtraction operation all use the exact same symbol. To talk about opposites, we tend to think about things in terms of parentheses. So if I want the opposite of 3, the result is -3. Right? With the parentheses, I read this as the opposite of 3. Without the parentheses, I read this as -3. The opposite of -5 is +5, and the opposite of 0 is 0. The absolute value of a number has the same value, but is always positive. If you try to take the absolute value, and to denote absolute value, we use vertical bars. Right? So if I want to take the absolute value of -7, the result is the same value, 7, but positive result. If I want to take the absolute value of a positive number, absolute value of 9, same value, 9, positive result. Absolute value of a negative number becomes positive. The absolute value of a positive number stays the same. And the absolute value of 0 stays the same. All right. Absolute value and opposite are two very different concepts that have somewhat similar basic ideas of keeping the same value and playing around with the sign. So pay attention and make sure you have straight which one is which. Again, very different concepts. Excuse me. Very different concepts, but because they both are playing around with the sign of a number, I often see students mixing the two up. We'll come back and look more at both opposite and absolute value a little bit later on in this video. The rule for addition with signed numbers is if you're dealing with two numbers with the same sign, you add them and keep the sign. When you're dealing with two numbers with different signs, you subtract them and you keep the sign of whichever one was bigger. The way that I think about this is think about positive numbers as plugs and negative numbers as holes. So here I have 3 plugs and 7 holes. Let's draw out those 7 holes. And let's draw out those 3 plugs. You can think about a plugged hole as canceling each other out. You had a hole, you plugged it, you no longer have a hole. So that's gone, and that's gone. And then we count the number of extra plugs or extra holes that we have. In this case, we have 4 extra holes. We have 4 of them. Holes are what I called negative. So 3 plus negative 7 visually should be negative 4. Following our rule, 3 plus negative 7. That's a positive number and a negative number. That's different signs, so we subtract them. 7 minus 3 is 4. Then we look, 3 is smaller, 7 is bigger, and 7 is the negative number. So that's another reason that we get the result of negative 4. Right. Similar idea, just one more example, 5 plus negative 2. Right. Again, I'm thinking about positive numbers as plugs and negative numbers as holes. So I have here 2 holes and I have 5 plugs. I use 2 of those plugs to plug the holes, and then I have 3 more plugs left over that I haven't used yet. Right? When you plug a hole, it fills the hole, uses the plug, so they cancel each other out, and you can ignore them. Those 2 things are gone. We have 3 plugs left over. Plugs are what we called positive numbers. So that's how we end up with positive 3 as the result here. 5 plus negative 2 is 3. Looking at our rule, we get the same conclusion. 5 and negative 2 have different signs, so we subtract them. 5 minus 2 is 3. 5 is bigger and 5 is positive, So our result came out as positive 3. I think it's a little bit more obvious how this works with the same sign. Right? 2 plus 3 is 5. That's just positive numbers. Nothing weird is going on there. But I've got 2 plugs. And then I've got 3 more plugs. So all told, I have 5 plugs. Same thing happens with negative numbers. If I have -4 plus -1, -4 is 4 wholes. -1 is 1 more whole. All told, that's 5 wholes, 5 negative things. The rule here says if you have the same sign, you add them and keep the sign. -4 and -1 are both negative. 4 plus 1 is 5, so -4 plus -1 is -5. The rule for subtraction is almost cheaty. The rule for subtraction is to rewrite the problem using addition. In algebra, subtraction doesn't actually exist. There are only 2 operations in algebra, addition and multiplication. Subtraction is a shorthand notation for adding an opposite. So if we have something that's written as some number A minus some other number B, the rules of algebra tell us that what's really going on here is we're taking A plus the opposite of B. And that's exactly how we're going to treat subtraction in this course. So if I have something like 2 minus 7, here's subtraction on positive numbers that we couldn't define based on what we've talked about in previous videos. Well, here, I can rewrite this. Instead of 2 minus 7, it's 2 plus the opposite of 7, which is -7. Then we can use the rules of addition. 2 numbers with different signs, we subtract them and keep the sign of the bigger number. 7 minus 2 is 5. 7 is bigger and negative, so the result here is -5. If one of our numbers in the subtraction problem is already negative, things can get a little bit messier. Three minus -4. Rewrite this problem as addition. 3 minus -4 is the same thing as 3 plus the opposite of -4. And the opposite of -4 is +4. And then 3 plus 4 is 7. So using this rule that subtraction is really addition in disguise means that we don't have a separate rule for dealing with subtraction. We just cheat and turn it into an addition problem, and then we can go from there. And yes, this really is the rule for subtraction. In algebra, when you're dealing with subtraction, you turn it into addition. In calculus, when you're dealing with subtraction, you turn it into addition. In graduate level mathematics, when you're dealing with subtraction, you turn it into addition. One thing that you have to be careful about, especially with signed numbers, is making sure you follow the order of operations correctly. Right? The order of operations tells you whatever operations you encounter reading from left to right between addition and subtraction is the one you go with first. So 3 plus 2 minus 7, the addition occurs first. This turns into 10 minus 2, which is 8. Four minus 7 plus 5. Reading from left to right, you encounter the subtraction first. 4 minus 7 is negative 3. And then negative 3 plus 5 is 2. Absolute value bars work as grouping symbols. If you have absolute value bars and you have operations inside, here we're taking the absolute value of negative 4 plus 9, you evaluate what is inside the absolute value first. Negative 4 plus 9 is 5. And then only after you've done that, you take the absolute value. Absolute value of 5 is 5. Likewise, with subtraction, if I have the absolute value of 3 minus 7, 3 minus 7 is the same thing as 3 plus negative 7, which is negative 4. And then only after I've done that, I take the absolute value of negative 4, which is 4. Up next, multiplication and division. These are two different operations, or so it seems. But as we'll see a little bit later when we talk about fractions, multiplication and division really are the same thing in disguise, or division is really a disguised way of talking about multiplication. And so because of that, it makes sense that the rules for multiplication and division are exactly the same. And the rule simply says that if the two numbers have the same sign, the result is positive. If the two numbers have different signs, the result is negative. So if I want to multiply 3 times negative 4, well, I know that 3 times 4 is 12, and 3 and negative 4 have different signs, so the result here is negative 12. If I want to multiply negative 5 times negative 3, I know that 5 times 3 is 15. Negative 5 and negative 3, they're the same sign, so the result should be positive. And doing division, the same rule still applies. Negative 24 divided by negative 6. Well, 24 divided by 6 is 4. Negative divided by negative are the same sign, so the result is positive. Negative 24 divided by negative 6 is positive 4. Introducing multiplication and division puts a new wrinkle into the process of worrying about the order of operations. For example, 4 minus 9 times negative 3. According to the order of operations, the first thing we want to do is 9 times negative 3, which is negative 27. Be careful here. Notationally, it's really easy to get mixed up and lose that negative sign. We have 4 minus negative 27. And of course, opposite of is, I'm sorry, subtraction is adding the opposite. So we rewrite this instead of 4 minus negative 27 is 4 plus the opposite of negative 27, which is positive 27. And 4 plus 27 is 31. All right. With multiplication under our belt, we can look a little bit more closely at the opposite of operation. This opposite of is really multiplication in disguise. The opposite of negative 7 is really trying to tell us that we want to multiply negative 1 times negative 7. 1 times 7 is 7. Negative times negative, same sign, gives us a positive result. The opposite of negative 7 is 7. The opposite of 12 is really negative 1 times 12. 1 times 12 is 12. Negative times positive, different signs, gives us a negative result. The opposite of 12 is negative 12. There are several places in algebra where this trick becomes very useful. For our purposes this semester, the place where we have to worry about this trick is a kind of unexpected location. That being in properties of exponents. If I want to evaluate negative 3 squared, the rules of exponents tell me that negative 3 squared is negative 3 times negative 3. 3 times 3, of course, is 9, and a negative times a negative is positive. So negative 3 squared is positive 9. A more complicated expression that involves an exponent might ask me to do something like take the opposite of 3 squared. Following the order of operations, I will first work inside the parentheses. 3 squared is 9, and then the opposite of 9 is negative 9. That's not too bad, I hope you agree. But very importantly, in both of these expressions, I have parentheses in the original statement of the problem. The question is, what happens if I leave the parentheses off? And there's no good answer here. It's not clear with the parentheses missing whether this statement should be read as negative 3 squared or if it should be read as the opposite of 3 squared. So what I need to do is teach you first of all, that leaving parentheses off when you're squaring a negative number is a bad idea. You shouldn't do it. I shouldn't do it. No one should ever do it. The second thing I need to teach you is that many calculators and most computer programs, when they see this, they interpret it as the opposite, not as negative. And because opposite is multiplication, this is -1 times 3 squared. -1 times 9, -9. If that doesn't make any sense to you, you're not alone. Again, as far as doing mathematics is concerned, the real answer here is you should never talk about exponents without putting parentheses to make it clear what you want. But it's also important in today's world of technology to understand what computers and calculators do. Normally, when we're talking about exponents, this is what we're trying to talk about, -3 squared. But most computer programming languages, and by extension, most calculators, do not think that way. The way that computers are programmed, if you don't have parentheses around it, it interprets that result as the opposite of 3 squared. So you should be aware that if you are working on an assignment in an electronic system and the parentheses are missing, that you should read that as the opposite of 3 squared. More importantly, you should be aware that if you are using a calculator or you are writing a computer program, you need to have parentheses there, otherwise something weird will happen, and you don't want something weird to happen. So make sure you're always putting the parentheses there. When the parentheses are missing, make sure you know that means that something bad is probably going to happen. This is going to be confusing and stupid and wrong. Right? Very much that is not mathematics. Right? This idea, wrong shoulder. This idea is not mathematics. This idea is computer science and accepting the reality of the world in which we live. These ideas up here that I apparently am getting clipped off when I try to point to, those are mathematics. Those are the things that you really need to be aware of, that I'm really going to worry about for this course. Right. So with that, there's a nice overview of the properties of exponents for you. There are several problem sets, several assignments in D2L waiting for you. So please take the time, work through those, practice all of these skills on working with signed numbers, and I'll see you in the next video.